All right, so for the review, things that will be on the test are on this review page. So I'm going to kind of work some out for you. Um, we'll come back to this extra one here, this business right here. We'll do that in a few minutes. It will start off, well, there'll be on there somewhere, there'll be a part where I probably will have an attached, an Excel file posted online that you'll download. You'll do a pivot table on it. You'll answer the questions from the pivot table. There you go. And then you can also use Excel for some of the things. But something along these lines, right? I'll ask you things like, hey, what's probably the person's female given it was mint ice cream? Well, it's 20 out of 80. Okay? Things like that. Remember, if the ratios are wildly different, then they are what we call dependent. So clearly, females in this case, and this completely not made up data, way prefer chocolate to men, but over here the men way prefer mint, and they way prefer Tin Roof Sundae, and they're half and half on the strawberry. I don't know, whatever. So when you do those sorts of things, that we would say that it's dependent. Okay, again, it doesn't mean anything other than the fact there's a relationship there. A couple of mutually exclusive events here would be chocolate and strawberry. You can't be both at the same time. Neapolitan doesn't count. And yeah, cool. Nice. If A and B are mutually exclusive, probability of A and B equals 0, obviously, because, you can't at the same time. Sample space. I may ask you to come up with a sample space for some small sort of thing. In this case, heads and a dice, or tails and a coin and a dice are pretty straightforward because there's only 12 outcomes. I would never make you do that for more than, let's say, 12, 16 outcomes, because that's just weird. And so I would never ask you to list out, how many different combinations of dinner there are. Hey, there's 20,000 combinations for dinner. Write them all out. That's ridiculous. Yeah. Clearly, the number 9, probably is you get a 6, given that its heads is 1 out of 6. That will dub. That's because they are independent, right? It doesn't matter. Probably getting a 6 is 1 out of 6. It doesn't matter what happened on the coin, on the coin there. Okay. So there's 31 marbles in the jar, looks like here, right? And so what's probably a green, given you got a black the first time, and this is without replacement. Yep, you put it in your pocket. So in other words, you don't replace it. So there's 30 marbles left. 7 of them are green. Probably get 2 green marbles. You get 7 out of 31 times 6 out of 30. Nice. And a blue and a red in any order. So you could do 12 out of 31 times 3 out of 30, or 3 out of 31 times 12 out of 30. Or, here's another way to do that problem, would be to say, all right, so you have blue marbles, there are 12. For some reason, my pen doesn't want to work. What's your freaking problem? Piece of crap. 12, choose 1, which is 12, obviously. And times 3, choose 1, which is 3, obviously. Over 31, choose 2. And that would also be another way to do this problem. So you do it the way I did it, or you could do 12, choose 1, times 3, choose 1, over 31, choose 2. Either way, 7% chance of that happening, almost 8% chance. Cool. Nice. Very interesting. Pretty straightforward. Just it's the first counting, or the fundamental counting principle. Piece of cake. Something like that could very well show up. Remember, you multiply the number of outcomes on each, and the number of choices, I guess the way I like to say it, at each decision point. Okay, you had this many 3 choices, and then you had 12 choices, and then you had 5, and then 3. 140 total outcomes there. Good question to ask would be this: are they all equally likely to happen? Or in other words, do we all use them all? Well, like on your wash machine, you may very seldom, if ever, use permanent press, okay, or the whatever, but you may use the extra rinse cycle a lot. Sometimes you wash a lot of dirty clothes, you can rinse them a second time and make sure you get them really nice and cleaned up, whatever. Maybe you do that because that's what you get dirty a lot, but really use the permanent press option or the delicates option, or maybe that's all you use is delicates. I don't know. But in other words, they're not all equally likely. Nice. Yeah, Yes, sweet. 60% belong to a union. All right, well, listen, that means 40% don't. So 0.4 to the fifth power. So you need no union and no union and no union and. And, of course, always means multiply. Okay? And then at least 1 was 1 minus 0.4 to the fifth power. So there you go. Remember, at least 1 doesn't mean all. It just means it could be 1 or 2 or 3 or 4 or 5 or 6. The only thing that wouldn't make you happy at all is if none of them were union members. Okay, so you just got to subtract that one thing out. The rest of them, you're golden. Okay, same problem. The next 13 is the exact same, basically, as the one up above. 12 choose 0. I don't want any of the Democrat ones. 16 choose 2. Okay, 4 choose 2. 3 choose 1. Lovely. That's 5 total people are selected out of 35. And there's your answer right there. Nice. Now, on this next problem, 14, either one of these I would have accepted either answer if we have the same questions on our test, but they're in a different order. If you had said to me, hey, I think that's a different test, I'd be okay with that. Therefore, permutations would be what you would have gone with. And if you'd have said, hey, that's the same test, I don't care how many different ways you can reorder the questions on the test. If they're the same questions, it's the same test. And if that's the case, then you would have said to me, oh, that's a combination. Okay? And so, and in either one of those, I'd be okay with as long as you explain it. The question like that, it's pretty common for me to do a problem like that on the test where it's a little ambiguous because I want you to say, well, it depends. Okay, cool. What does it depend on? Okay, and then I want you to explain to me, oh, yeah, it depends on this or the other. Okay? 2 letters, 6 numbers, 26 to the second power times 10 to the 6th, 676 million possible outcomes. Okay, now this one here, every time I put something like this on the test, people will get out. This one, it says 30 people waiting with you. So somebody told me once, a couple people said, well, that means there's actually 31 people in line, Jay. And I went, just a minute here, let me pause for a sec. Anyway, everybody, I've had questions similar to this on a test before, and people will be like, there's actually 31 people in line, including you. And I went, oh, brother, whatever. If that's the case, I would never mark you down for that. I went as if you were one of the 30 people. So life goes on. 17, pretty straightforward. I may very well ask you to come up, well, see, like 18, come up with your own PDF. Okay, but here's a PDF. You're going to find a C that makes this work. So for me, my C would have to be my A, or, oh, I'm sorry, I wrote it as A. It should be C right here. Would have to be 6/7 to get that to integrate to 1. And the probability that you are less than 0.6 will be the integral. And then you get 27% chance of it happening. Another question I could ask on this, guys, what's the expected value of x? And so, of course, that would be 6/7 integral 0 to 1 of x times 2x squared plus x dx. That would be the expected value of x. That would be an excellent question to ask, although I think I asked it down below. So now that I say that, I don't know, whatever. Come up with your own PDF. This piece here is for the next question. So come with your own. Remember, it has to integrate to 1 over a specific integral. So that's cool. And I personally don't. And so it has to integrate to 1 over a specified interval. Doesn't really matter what the interval is to me. I don't really care. It can't ever be negative. Remember that. So it can never dip below the y-axis or the x-axis. If it does, that would mean we have negative probability. And that would be, not optimal. Okay. For this one here, it's pretty straightforward. I just worked it all out. They're either high school dropouts or they're whatever. Okay, great. And then they're either male or female, all the way down the line. So now it says if a person selected at random was probably the person has a master's degree or a bachelor's degree, given they're female. So everybody on the bottom, those are all your females. The ones on top are the master's and bachelor's degree females. So there's a 46% chance. Okay. There it is. So there's our CDF. Remember the CDF, if you're going to do a CDF, make sure that you put in different variables here and then you integrate from 0 up to x. Oh, look at that. Expected value. And there's our variance down here, of course. Okay. It's like I know what I'm talking about without talking about it. Right. So on this next one down, remember to find expected value here. You take your x's, so 1 times 200 over 500 plus 5 times 122 over 500, etc., dot, 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 dot. 5342 is our expected value. And then, of course, the expected value of x squared would be 1 squared times 200 over 500 plus 5 squared times 122 over 500, dot, dot, dot. And then the variance is the difference in those two variables. Okay? Cool. Okay? Clearly, if a guy were doing this, and this is the final. There's your variance. If you wanted the expected value to be a fair game, you would bet that much right there. In other words, you'd expect to get 0. The expected value, if you want it to be negative, the expected value was of the fair. If you played a game and the expected value was 0, that means you break even. You never make any and you never lose any. By the way, no one likes these games. When I was a kid, my grandma bought this game, and she thought it would be so much fun for me and the kid, and my cousins to play. And she broke it out, and we used to play like, I don't know, Hungry Hippo and Mousetrap, and I don't remember all these different Life and Uno. Well, we couldn't play Uno because she was very much against card games. But whatever. Anyways, Anyway, so this one comes out, and it was called the Ungame, and there was no winners and there was no losers. It was the very first, I guess, woke kind of game or something where like everybody's a winner, man. And I remember playing it once, and I said, "Yeah, I'm never playing this again, Grandma. It's not a game. We play basketball, we play football, we play a lot of games. This isn't much of a game. You want to play a game where the expected value is negative, okay? That is, you expect to lose over time because when you win, if you win, you're happy, okay? Nobody wants to play a game where you win all the time. It's boring, okay? Oh, look, I win all the time. Well, first of all, no one's gonna ever let you do that, like unless you're a little child, okay? So no one's gonna do that. The fact that you break even, no one wants that. The idea is you want to overcome, right? That's the whole thing, right? Oh, I'm the underdog. Oh, yay! And then, I overcame and I won. Yay! The crowd goes wild. That'd be cool, okay? But no one wants to play an expected value that's 0. That is a fair game. No one wants to do that one. Okay, now I'm going to copy this one to the next page here. So this guy right here. And I'm just going to work through. Well, I said I was. Darn you all to thunder. Maybe I can. Well, it says 3 over 128 xy squared. I'm just going to go to a new page. 3 over 128 xy squared. And then x goes from 0, 2, and y goes 0, 4. Okay, so questions that I will ask you. First of all, is it a PDF? Let's find out. So we're going to integrate. Let's see if we get 1 like we're supposed to. Okay. Remember, the whole idea here is that means that some of the probabilities is 100%. If that's not true, then that's screwy. Somehow you've invented negative probability, or there's another. In other words, there's a bunch more outcomes that you just negated, or you said they don't exist, and that's weird. So I'm gonna do 3 divided by 128, and then x times y squared, comma x, comma 0, comma 2, comma y, comma 0, comma 4. Yay, it works. Woohoo! All right, so we'll ask you for things like, what's the marginal of x? I don't know, let's find out. So the marginal of x, we're simply going to integrate the y's out. So get in here, get rid of one of the integrals. Not that one, though. So if I want to get rid of the, boom. So x over 2. That is, I integrated the y's out. If you want the marginal of y, I'm going to integrate the x's out. So, just come back in here, make that 0, 2 this time. Come on, move, you hippie. And I get 3y squared over 64. Of course, the person could ask, are they independent? Well, if they were independent, then x over 2 times 3y squared over 64. The question is, does it equal 3 over 128xy squared? The answer is check. It does, yes. That means they're independent. Okay, remember, if the product of the marginals is equal to the joint, then they're independent. But remember, that's an if and only if statement. So if I tell you they're independent, that's true. If you show that's true, then you've proven that they are independent. Okay? Now, do a variety of other things. Expected value of x. A couple ways to do it, of course, is you could do x times xy squared dx dy 0, 2, 0, 4. You could do that. But that's equivalent to doing 3 over 128. No, it's not true. It's a lie. That is a damn lie, Jay. Don't say that. Don't you say that, sir. Right? So you could integrate the marginal of x from 0 to 2 dx, and you get the same thing. Okay? This is exactly the same. Where'd the y squared go? Well, you integrated it out before, right? I guess these have to, you'd have to flip-flop these around. In other words, what happens, we just did the inner one first, and then we ended up here, as in essence of what had happened, right? If you get the same answer regardless, but I'm saying to get to here, you would flip those around. You'd have done dy first. You would end up here, and that's why they are the same. Okay. So if I said this, say what's the expected value of x? Well, it would be the integral of x times this dude with respect to x from 0, not from 1, you jackwagon, from 0 to 2, like 4/3. That's hot. And if you wanted the expected value of x squared, just for a good time, again, it's the same thing, just make that x squared. And in here, you just change that x to an x squared. That's why I don't try to do it all in my head. I can just, because I typically want x and x squared. So it's 2, that's hot. So if I want the variance of x, it's going to be 2 minus 4/3 squared, which is, that'd be 16/9. This would be 18/9. So minus, so 2/9 looks like would be my variance. Of course, if you're playing along, you're like, oh, but I want the standard deviation. So square root of 2 over 3. There you go. Hope that makes you happy. Expected value of y, same principle. It's just obviously integrate with respect to y. Or you could just use, again, the marginal of y, which is what I'm going to do, I think. So I'll go up here, integrate the marginal of y, which is that fella. Oops, but wait a minute. Come back here. Put y times that first, dummy. Y times that, babe. With respect to y from 0 to 4. Let's go. Here we go. 3. And the expected value of y squared. Come back in there, make that a y squared right there. You get 48/5. Nice. I don't understand these pens. Now the other one wants to work. I don't know. So the variance of y is equal to 48/5 minus 9. It's y squared, and so 48/5. Clear, grab that fella, minus 9 is 3/5. Isn't that sweet? Nice. All right, things like this. You could do covariance. Hey, what's the covariance of x and y? Remember, that's the expected value of x and y minus the expected value of x times the expected value of y. I'll tell you right now, it's going to be 0. How do I know that? Because they're independent. Okay, that's another way to say that x and y are independent if this is true. And so you're going to have 3 and you're going to have 4/3. 4/3 times 3, which is 4, which means the expected value of x and y is going to have to also be 4. Check me, let's find out. Okay, so the expected value of x, y is just the integral of just like that. Anytime you say expected value, could I find the expected value of 7? Well, it's 7. But yes, you could totally do that because you just throw a 7 in front of it. Or, like, what's the expected value of j? Oh, it's j. How do you know that? Well, you throw it in there. It's a constant. And if you integrate this thing with respect to this stuff here, right, this stuff's going to integrate to 1. Now, in this case, because you threw x and y in there, all right, expected value of x, y, this is how it works, right? But x, y are not constants, and so they're obviously going to change when you do this problem. But expected value is always expected value. There's nothing fancy about expected value. It's always whatever it's the integral of whatever you're doing, of whatever you're trying to find the expected value of, times your PDF. And yes, you could combine those if you like. I don't, but you do you. Four? No way. Check it out, dog. 0 covariance, which means they are independent. Okay? That's what your test is going to be like. Pretty straightforward. Don't overthink it. You can have a page of notes, front one-sided page of notes. And yeah, that'll be a good time. All right, bye.